It's a paper about adjudication of conflicting claims, and one of the questions I'm looking at, or the main, is how to liquidate them orderly. So probably many of you know what is called the what I call the simple claims problem, when there is a single debtor and several creditors. That there is evidence that you have complex liabilities and claims within the financial system. And it has been clear since, in particular, the bankruptcy of Lehman Brothers. So basically, I want to study rules like a social choice problem when you have to liquidate cross liabilities, okay? And so this is a point of view of a regulator, where you try to define, before knowing what type of what problems you will face, what will be the solution. Okay. And maybe surprisingly, I mean, I'm just looking at the problem of defining proportionality. Do you hear me? Well, it's okay. So proportionality is very easy to define in the simple claims problem, but it's much more complex when you have cross liability, because first you have both you reimburse and you are repaid, so it's not clear on which entities you define proportionality. And also because what I am looking at, and it's one of my main interest, is that I am looking at a system of financially linked institutions, but that have relationship with external creditors. So this means that what is happening in the system, I mean, has an impact on external creditors. And what I have in mind, of course, is a case of banks, for example, which have relationships between them, but which may default on, say, their deposits. So the deposits are the external creditors. And the main objective of the regulator is to avoid this default on external creditors, or this is what I am assuming. This is what I call no bankruptcy. So I will model as very stylized problem. I mean, where basically I have a matrix which is given by the claims and liabilities, and one need to transfer this matrix into a matrix of transfers. And I characterize the proportional rules either through considering the optimization of a fairness criteria, which is the entropy here, or through axiomatization. So I skip, maybe I can come back, but given that just 20 minutes, it's, so I will introduce the model and define, consider different types of rules. And for each situation, it turns out that one has different proportional solutions. So depending on the constraint, either informational or additional constraints, one may want to consider. So the liquidation model is, so as I said, it's very stylized. There is just a single liquidation date. I have n firms or banks or whatever. And so they have cross liabilities between them, and which are represented by the amounts that each has owed to each other one. Of course, it can be null, so it is Lij. And there is an external value. So this represents the relationships with outside world, and which is summarized in Zi, which can be positive or negative. So one can think of Zi as a difference between the external assets and the external liabilities, for example, external deposits. So it's just, the data are just given by the Z, the external values, and the bilateral liability. So it's relatively simple. And for considering resolution rules, I also consider the case where the regulator does not know the full bilateral liability, so the full matrix, because it is sometimes the case, or it has limited information on the bilateral liability. And in that case, it means that the problem is given by the external values, the total liability, and total claims for each firm. And then one can define either coarse or full rule. So a coarse rule is just to the regulator assigns to a coarse problem firm must repay or will obtain. So BNI is how much I will be repaid, the sum of what the other give to I, and BIN is the sum of the reimbursement made by I. And the full rule, when you have full information, you just assign bilateral transfers. So in the case of full rules, it's just you have this matrix, Lij, and you transform it into the Bij. And what matters, of course, are the external values. I mean, what may influence the solution. So I will explain what is this objective of avoiding default on external creditors. And so I is not bankrupt if, so AI is its external asset, BNI is what it received from inside, and BIN what I must give. Okay, each time I have this notation, it's a sum. Okay, and so basically the condition says that the external asset plus what it receives from other minus what it gives is larger than the debt, outside debt, the deposits. And it can be written as the sum of the external values plus the net transfer is non-negative. So W is for wealth. Okay, this is why now one can forget AI and DI and just concentrate on this net external value. Okay. So it's a simple claims problem. I mean, there is not such constraint because creditors, whatever they receive, they are not bankrupt. In very simple. So you could say, well, what is the problem actually? Why you don't simply specify transfer that are exact, which means full. So I have written here on the aggregate repayment. And just the problem is that if a firm is distressed, what I call distressed, then it will be bankrupt as this exact allocation. And distressed means that the net external value plus what my claims minus my liability are negative. I am not able to reimburse fully, even in the best possible case when I am fully reimbursed. Okay, and so this is exactly the problem, is that when you have distressed firms, if you want to avoid bankruptcy, and how you do, because then you distribute some losses to the non-distressed institutions, and they can become bankrupt as well. Okay, so in some sense, a rule will try to avoid bankruptcy as much as possible, and so it is in this sense that it is an orderly liquidation. Sometimes it's not possible, of course, it depends. So I just recap what I call solutions. It means an allocation such that no firm is bankrupt, and a rule, which can be coarse or full, assigns to each problem. I don't specify for the moment what is F. it will depend on the constraint. And it must assign the exact solution when there are no distressed firms, but otherwise it assigns a solution. Okay, just maybe to illustrate here. So it is simple in the sense that, so I have 3 firms. And as you see, the total liability, for example, if you consider the first row, you have the liability of 1 towards firm 2. The liability is 1, and liability of A to firm 3, and so on by rotating. So it turns out here the total liabilities is equal to the total claims for each firm, and they are identical. So this simplifies a lot. So, and the external values. So 1 has a negative external values, and it is distressed. Okay, because it's easy to compute, because its net liability minus claims is 0. So, I mean, it's distressed. I mean, you can have distress, you can have firms with positive external value, but which are distressed. It depends on. And so, just to understand the difference between coarse and full information, under coarse information, the regulator cannot distinguish between firm 2 and firm 3 because they have the same net external values and the same total liability and the same total claim. So they should receive the same amount. And under full information, now, for example, if you take A smaller than 1, 2 has, he has land, when you want to look at the landing, you look at the columns. So 2 has land 1 to 1, and A, which is smaller, to 3. So 2 has land more to the distressed firm, and so it might be penalized for that. But on the other hand, 3 has borrowed more from 1 than 2. So maybe it should be penalized as well. So this is why it is not that clear, I mean, to define a solution. Just the last definition, I will concentrate, and actually it's a point I would like to investigate more after, is on what solutions that I call tight. So they are bounded in the sense that you bound the reimbursement and repayment by the corresponding liability. And you force each non-distressed I to reimburse fully its liability, and you force each distressed I is reimbursed fully. So this is a question which is, I mean, sometimes it's imposed by the 2 conditions, is imposed by some regulation, but not all, because, for example, in the case of Lehman Brothers, in the US, a bank on which Lehman has defaulted should nevertheless fully reimburse Lehman. And it was not the case in UK. So it has some, it's a regulation which may be discussed. And the super tight is, I just add that the distressed firms' net worth is null. Okay, they cannot end up with a positive. There are rescues, they default, and they cannot end up with a positive. So basically, these 3 conditions are to limit some form of contagion or some form of impact of the distressed firms a priori in some maybe arbitrary way. Okay, how much time do I have? 10, no. Oh, okay. Okay, so I will just describe the coarse constraint proportional solution because they are easy to describe. And just to, the regulator collects the full liabilities of non-distressed firms. He fully repays the liabilities to the distressed firms, which must give back the maximum they can because I want their net worth to be null. And in such a way, you are sure to have a super tight solution. So this means that you transform the problem into a simple problem where now the regulator has some amount, must use to reimburse, to repay the non-distressed firms, but he has less than their claims. And what I call constrained proportional is basically that you distribute, the regulator distribute in proportion of the liability, except if this would make one bankrupt. Okay, so basically it's a kind of, you have a proportion delta of the liability, but sometimes J receive more than this proportion delta because otherwise it would be bankrupt. So this means that I call mu J rescue index because basically it's equal to 1. It can be larger than 1 only if otherwise the firm would be bankrupt. Okay, I don't see. Okay, so I characterize this solution by minimization of an entropy index and by axioms. I just want to say that here I minimize the index over just the bounded solutions. So this means that minimizing inequality in some sense force the allocation to be tight, which means the distress to non-distress to fully reimburse and things like that. It will not be the case now under full information. So under full information, the regulator knows the bilateral values. And now one thing to say is that information is not necessarily, does not necessarily ease the solution, okay? And the reason is that, at least what I consider, that information imposes natural relationship between bilateral liabilities and transfers. And in particular, a firm I may not want to reimburse J if it has not borrowed from J, or he may not want to reimburse more than what it has borrowed. Okay, so there are two cases. Bilateral bounded is stronger than liability condition. So these conditions are more, again, like legal conditions. So I have no time to, the existence of bilaterally bounded or liability compatible solution in tight, I mean, you can transform that problem into existence of a feasible flow. So, and you get some inequality to be satisfied. And of course, they are stronger and stronger. Liability compatible is stronger than coarse and weaker than bilateral. Okay, so I come to the definition of proportionality when I just require liability compatibility. So what is this entropy index? Just to be more precise, it's a sum of a combination of, so Bij is a transfer of I to J, and the log of the ratio of Bij to Lij. So it has been used in many different problems to define fairness. And for example, if I did not have bankruptcy constraint, and I just say I have a total amount to distribute, and which is less than the total liability, if I minimize entropy, I distribute everything proportionally, full proportionality. But here it will not be possible, not necessarily, because of the bankruptcy constraint. Okay, so the first problem I look is when I just require liability compatible. So I don't see whether the message. So.
I think you have about 3 minutes left.
Okay, so I characterize basically, I mean, these solutions are constraint be proportional, and which means that basically the transfer are determined by defining a kind of reimbursement ratio, which is my delta I. But now it's not really the same ratio of reimbursement to all firms, because one has to take into account that a firm J, to which I reimburse, may become bankrupt if I just reimburse everybody the same proportion, in the same proportion. So this is why one obtains a bi-proportional solutions. And again, the rescue index is larger than 1 only if it is needed to avoid the bankruptcy of J. And so I have some axiomatization. I just show you the form when you have bilaterally bounded, just to tell you that it's a kind of truncated version of bilateral solution, and which means that now you have again some indices. One delta I, the capacity of reimbursement. Mu J is your rescue index, or the G's rescue index. And since you want Bij to be smaller than Lij, now you take the minimum of the product of these two indices, of ability of I and rescue of J, the minimum with respect to 1. So it's kind of truncated version. And I wanted just to illustrate that the two solutions under full information differs. And but maybe I have no time. I should stop, no? Or okay, I'm sorry. just to finish, just concluding remark that just I was trying to define proportionality to liquidate cross liability. And one of the main results is that one should differentiate creditors according to their health. I mean, it's usual to have that the reimbursement depend on the health of the borrower. But here, because all this cross liability, you distinguish between the capacity of reimbursement and the capacity of being not bankrupt. And this is why you have these two indices. And just because it's a computer science, so this solution, usually you cannot compute them by hand. But since it is an adjustment matrix problem, I mean, I'm not fully studied that, but one can adapt the algorithm of adjustment of matrices, which are known scaling algorithm or fitting algorithm. But sometimes there might be problem when you have too many zeros. Okay.
Thank you very much. Let's unmute our mics and give a round of applause. The earliest question I'm seeing on chat is one from Yair. Yair, you want to go ahead and ask?
Yeah, no, it's a very interesting topic. I'm just wondering whether you have explored also, why not take kind of like a naive approach here and just decompose this problem into like a bunch of single bankruptcy problems where, okay, if I owe money to a bunch of people, I'll use some standard solution like proportionality or the Talmudic solution or whatever it is in order to divide the money and basically treat each one of these instances as its own and disregard what is happening in the global system.
Yeah,
like what would happen then? Why would that break?
I had no time to introduce my axiom, but basically one axiom is, well, I mean, it's called consistency. And the thing is that what you suggest is that when I reimburse some other firms, I mean, their bankruptcy constraints depend on what they obtain from the other firms. So all these problems are not independent. And in some sense, you can see the solutions as, okay, requiring what you suggest. I mean, each firm in some sense reimburse kind of constraint proportionality, its liability. But the constraint in phase depends on all the other And this is the indices in some sense are handling that simultaneously. Yeah.
Haris, you had a question about a cooperative game.
Yeah, I mean, for example, I agree, I mean, in the simple claims problem, I mean, there were these two approaches by axiomatization and some by cooperative games. And actually, I've not tried. And because I had more the point of view of a regulator. So that's true. I mean, it's not, I think in some sense, consistency sometimes is a form of saying cooperative approach, in the sense that you assume that the reimbursement of some other firms are fixed, they leave, and then you apply your solution. But so if cooperative games is to accept a solution for a subgroup, I might have difficulty for that when I have cross liability, because everything is interdependent. But it's another possibility, of course. And it would not pin down a solution, probably.
Thank you.
Vincent Conitzer had a question. Is there anything to be said about incentives that this gives the firms?
So this is a big problem, I think, already for the other. I think here the incentives are relevant if you consider ex ante, how this liability and claims. It's probably the most relevant question on incentives, is how this liability, where do they come from? And in that respect, actually the solution I propose, I had not time, but there is another which has been defined by Eisenberg and Yair, where you have not these rescue indices. And here, in some sense, what I like, but it's not that I don't take the problem like that, but is that you have to reimburse more a creditor who is in difficulty. So this means that in some sense, it takes a little bit in consideration the fact that when you borrow, you may put others in difficulty. And usually it's not like that. Okay, I have money, I don't care about the health of my lender.
I see a question from Tushant Jat. Are there some guarantees that this form of resolution can satisfy in terms of some notion of overall health of the aggregate system?
A guarantee of, I don't know whether it's that answer. I take as, I impose that whenever it's possible to avoid the bankruptcy of a firm, I mean, one takes a solution. So implicitly, this means that bankruptcy is very costly. I am not comparing, I mean, what happens in with this solution and with the cost of that would be imposed by bankruptcy. So I'm not sure it's the answer to the question, but so in some sense, it's just implicitly assuming that default on, say, deposit itself may create a very large cost. But of course, it's a natural question here. What could?
Okay, I think this will be the last question then from Benny. He asks, how does this compare to the resolution proposed by Eisenberg and Yair? Is there a difference?
Yeah. Okay, so so I had no time. I knew that I would be short. So Eisenberg and Yair, this is they have the mu J, my rescue index. I have no rescue index. So they require that you reimburse all your creditors in the same proportion. And so this means that the solution differ quite substantially. In particular, Eisenberg and Yair may have bankruptcy which could be avoided. And in other case, I have not a solution, and Eisenberg and Yair But in practice, I'm not sure that Heidenberg and Noe is a good assumption. Because, for example, Greece did not reimburse all its creditors in the same way. Not at all.
Okay, let's thank the speaker again. We'll be moving to break. Gabrielle, people had lots of interesting questions, so you may want to take another look at the chat.
Okay, okay. I will be able to read them tomorrow, or I don't know, or other day.
I'm not sure of the timing, but we'll get them to you in one way, shape, or form.
Okay.
So I think we're going to be moving to, you have the option now to go to a breakout room for 10 minutes, and then we'll be reconvening for Yair's presentation.
Bill, are you there?
Yeah.
Oh, let's continue, I think.
Are people back from the rooms?
Yep.
Okay, welcome back, everyone. Our next speaker is Yair Zick. Yair is a computer scientist at National University of Singapore, where he's an assistant professor. His research fields are computational fair division, computational social choice, algorithmic game theory, and algorithmic transparency. He's received the 2011 Amos Best Student Paper Award, the 2014 Victor Lesser Dissertation Award, and the 2016 ACM EC Best Paper Award. And he'll be speaking to us today about a learning framework for distribution-based game theoretic solution concepts. Welcome, Yair.
Thank you. Thank you, Bill, for the introduction. And can everybody hear me? Are you all good? Yep. Excellent. Good. Yeah. So today I'm not going to be talking to you about one paper, but about maybe a few of them together. So I lied in the abstract, but you'll forgive me. So yeah, so my name is Yair. Right now I'm at the National University of Singapore. I'll be moving to University of Massachusetts at Amherst this fall. Well, COVID-19 notwithstanding, and this is what I think is a really interesting line of work that tries to bridge between two interesting fields. Right. So because I don't have a lot of time, I'm going to start at the beginning. So it is 2014, and I have just graduated with a PhD, not in computer science, in math, and you know, I was quite happy, right? So I've learned so much about cooperative games in my PhD. I wrote a thesis, everything was good. And then I started thinking, okay, so how can we take all of these nice theoretical ideas that we had during these 4 years that I worked with Edith and apply them in real world instances? And I started thinking about this. And as I was doing it, I was already moving to Carnegie Mellon and Carnegie Mellon University to be a postdoc there. And you know, you start reading faculty profiles, and everybody's doing this newfangled machine learning stuff, right? And I was really interested in that, and it kind of seemed to be an interesting and natural bridge to make, right? So here's the general idea and what we'll be really talking about today. Okay, so we have some game theoretic solution concept in mind, right? And hang on, I'll just open the chat here on the side just in case there's something surprising. Anyway, so I want to compute some game theoretic solution concept on a real instance. And what we usually do, right? We look, you know, if we're extremely lucky, we get a nice data set of game theoretic instances. We'll talk exactly about what that means in a second. But we don't get a lot of information about what people's preferences are, right? So a game, in a very abstract sense, is like, you know, we have a bunch of people, everybody has a preference order over some outcomes, and that's what the data would look like. It would look like, here is an outcome, here is how people like it, and a bunch of those instances. And what would you do? Okay, so if you ask a person who does machine learning, what they would tell you to do is this. You take the data, you partition it using like some random sampling into test data, into training data. You take the training data, you use it to learn a bunch of preferences, right? So you basically approximate people's preferences based on the data. And then you, you compute a solution based on for those preferences, right? But what I will try to convince you of today is that this might not be the optimal thing to do. Okay, there's a lot of reasons to want to learn people's preferences directly. There's a lot of literature about that, right? So it's not like I'm completely ruling it out. All I'm saying is that there might be a reason where you want to just go directly, right? You want to take the training data and you want to learn a solution, okay? And intuitively, what you want to do is that the solution that you compute in either case, whether you go through the preferences or you don't go through the preferences, that would be good with respect to the test data, right? With respect to the data that you didn't observe. Okay, that's the general idea of this talk. Okay, and why is this a good idea? Okay, so here's just a broad idea of why is this a good thing to do. Okay, so learning preferences, right? It could be very difficult, right? So if you think about a lot of you in the audience right now are you do something presumably with respect to a computational social choice, fair division, game theory, and stuff like that, and you know as well as I do how complicated, combinatorially speaking, people's preferences can be, players' preferences can be. Okay, so if they're complicated, it means that they might be hard to learn from a formal learning theoretic sense, right? So they have a what's called a high VC dimension or a high pseudo dimension. Okay, and the second point, which is slightly more subtle, it's actually really interesting. It says that exact solutions to approximate preferences may not be approximate solutions to exact preferences. Okay, so in machine learning terms, it just says that that if you approximate the preferences and then you learn an exact solution for that learned preferences, the computed solution that you have might not actually be an approximate solution for the data set that you have. Okay, so you might get a lot of errors in that data set, which is very bad. Okay. On the other hand, learning solutions, at least from the work that we have done, in some cases they might be easier to compute than to actually directly learning the preferences. Okay, so the structure, the underlying structures of the solution space is simpler than the underlying structure of the preference space. And because you're learning the solutions directly, then they're guaranteed to work probably. And probably here, I mean just on a high percentage of the instances. So having a what's called a low test error. All right? And we started doing this on, well, my PhD topic, right? Cooperative games. Okay, so for cooperative games, what do we have? We have a bunch of players, and each one of these sets of players has a value. Like each set of players, each coalition generates a value, an intrinsic value. Okay, so what would our data set look like? It would look exactly like that. It would be like a bunch of people, right? So a bunch of subsets of players, each one of them generating some revenue. Okay, so these three people here, they're valued, if they work together, they make $8. These two people here, if they work together, they make $5. These three people here, if they work together, they make $12. Okay, and you get a partial observation, okay, maybe not 3 instances, maybe a little more, but you get a partial observation, and these are generated by some unknown function v. Okay, you don't know what the function is, but you know that it's generated by some function. What do you want? Okay, what is your solution here? You want to find a pair of division x, right? So just a vector, right? So where xi is the amount of money that you're giving to player I, okay? Such that, and this is what the guarantee of the solution, okay? The original guarantee from the game theoretic literature says that each subset of players, each coalition, is paid at least its value. Okay, V of S. So the total amount of money that you pay each set of players is worth at least its value. All right. Now, what we're going to do is we're going to relax that guarantee. So that was actually the first kind of fun part, because this was the first time we did it, right, back in 2015. And what we wanted to do here is to just say, well, okay, we sampled a bunch of data from this data set, right, to get our training data. And what we want to do, the guarantee we want, is that the probability, okay, that for the sampled subset, so we sampled the set from some distribution, the probability that this set is paid less than it's worth, okay, strictly less than it's worth, is very low. Like, it's not very likely that this would happen, that this bad event would happen. All right, and then we kind of started exploring this space. We played around with it, and we looked at the various classes of games, because what was interesting to us at the time was to say, okay, some classes of cooperative games are easily learnable from samples, some of them aren't. Okay, could it be the case that there are classes of cooperative games that are difficult to learn, right, from a learning theoretic perspective, but you can actually compute such a pair of division using a polynomial number of samples. So polynomial here in the number of players. Okay, so we want not in the number of not in the number of subsets of players, because that's exponential and that's cheating. We want it to be in the number of players. Okay, and what we actually got is a piece of really good news. Okay, so the theorem we have is this. It is possible to find a pair of division x, okay, in polynomial time, and actually using, it's not exactly O of n time, so this is, I'm slightly lying here. It's a conceptual typo. It's actually using O of n samples, okay? So you can use a linear number of samples and the number of players in order to find a pair of division x such that this guarantee holds, this probabilistic guarantee holds, such the probability that a set of players gets paid strictly less than its value, the probability of that event occurring is really low. Okay, for those of you who know a little bit of machine learning, then the reason that this works is exactly the same reason that you can learn a linear classifier using a linear number of samples. It's exactly the same reason. Okay, but here's the deal, right? In this framework, you can totally cheat, right? And what do I mean by cheating? Let's say that I know a secret, and the secret that I know is that, well, the maximal value that you could actually obtain, like that these players could ever obtain, is $100. So here is a silly algorithm, right, that would work out. Just pay each player $100. That's guaranteed to stabilize any game whatsoever. Okay, so what we added is this little extra guarantee, which just says that this payoff division actually satisfies that the total payoff is weakly less than the cost of stability of the game. Okay, where cost of stability, I'm not going to get into it too much, right? But it's basically the least amount of payoff that you need, the least amount of money that you need in order to make the game core stable. So this is basically as good as you can get it. Okay, so I was really happy. This was kind of around the time that I was ending my time with Ariel and Anupam at Carnegie Mellon University, and I started my position at NUS, and I continued working on it because it was interesting and it was fun. And we started looking at a slightly more general class, and this is of hedonic games. Okay, so in hedonic games, what happens? We still have coalitions, we have subsets of players, but now each subset of players, its value is not a single intrinsic value, but each member of the coalition has an intrinsic value for that coalition, which is subjective. Okay, so if this coalition forms, right, then this person here has a value of 4 for it, this one has a value of 3, and this one has a value of 3. Okay, if these two people are together in a group, then this person has a value of 5, and this person has a value of 1. Okay, and again, these evaluations are taken from some unknown player preferences. So the player preferences are a secret, okay? Maybe what I will be willing to tell you about them is a little bit about their structure. Maybe I will tell you, okay, I'm not going to tell you how the preferences are generated, but they're additive, or they are top responsive, or they are a best player, best hedonic games, and so on. What is the solution concept that you want to get here? You want to get a partition. So if before in standard, in transferable utility cooperative games, you wanted to find a vector or payoff division, here you want to partition the players into disjoint groups, like this one right here. So here, these two people are in a group together, this person is all alone, and these two are together. And the guarantee you want is that, okay, if now you've observed this is your training data, right? So for your test data, if I sample another set randomly from the test data, what I want it to be the case is that it won't block this partition that you've generated. And by blocking it, I just mean that it probably with very high probability, it contains at least one player that prefers its current group, which we call pi of I, to S, okay? Or in other words, the probability that the bad event, that for every player I, the value that I assigns to S is strictly more than the value that I assigns to the partition, to the coalition that he was assigned, is, so everybody basically agrees, everybody in S that you have sampled agrees that it's better to form S, and then they will break out and leave, right? The probability of that bad event occurring is actually low. Okay, so that's very nice. And here, the picture seems to be a bit more complicated. Okay, it actually really depends. So, so whether a class of cooperative games, of hedonic games, sorry, was learnable was really depending on what kind of class we had. And here, one of the interesting things that we had is that, okay, so one of the questions that we asked, if you remember before, is, okay, suppose that I'm able to learn a class of games, okay, can we stabilize it? Okay, so in the TU games setting, the answer was yes, because, well, any class of games was stabilizable. Okay, but here this was not the case. So you could have instances of classes of hedonic games that you could learn the preferences, but you could not stabilize them. Basically, this robustness issue that I talked about before arises. Okay, so this is in particular for additive preferences. They're learnable, but they're not stabilizable. But other classes like top responsive preferences, they're not learnable. Okay, so they have a very high VC dimension, but they are stabilizable. All right, so just let me give you a very short example of what goes on here. Okay, so I'm going to look at a subclass of top responsive games, which are called B games. And here, the value that a player has for a set S is just the value that it assigns to the most favorite person in that set. Okay, so I don't care about the members. I just care about one person, like my favorite person in that set. Okay, my best friend. And then if there is like a few of them, then I break ties in favor of smaller coalitions. Okay, but that's kind of a small thing. Okay, so how do we resolve this? Okay, so I'm just going to give you the algorithm, and because it's actually quite nice. So what do? You need to basically compute for each player their probable favorite. Okay, so who is your best person in this group, in the initial group? So out of all of the people here, who do you like the best? Okay, and this basically you need to make an argument that this requires a polynomial number of samples. Actually, it requires a linear number of samples. Okay, and you do this for every player. Okay, and then what you do is you look for a small cycle here. Okay, so basically you say, okay, well, this person loves this person probably the best, and this person loves this person, and this person loves this person. So great, awesome. Let's just put them all in a group together. They're going to be, you know, this is going to be a coalition in the partition we generate. We're going to take them out. We ignore the errors we computed so far, and we recompute the probable favorites with respect to the new set. Okay, and if this algorithm, for those of you who do Donny games, if this looks familiar to you, it's because it's effectively the partial preferences variant of the actual algorithm used to compute a core stable partition for best games and for generally for top responsive games. All right, so that is amazing news. Okay, and then we kind of said, okay, well, we can get algorithms for some classes of Edoni games, but not for others. And then we said, okay, well, what happens if we actually look at the interaction structure? Okay, I'm going to slightly skip over that part, but basically the idea is that if we assume a certain structure where coalitions that are connected in this social network are allowed, but coalitions that are not connected in this social network are not allowed, then we can actually exploit this structure to get some polytime pack learnability results. Okay, and even so basically we can characterize the class of social networks for which this works. That basically is trees. Okay, and we, even if we don't know the structure of the tree, then we can rely on a result by Konitzer et al. From 2004 to show that even if we don't know the interaction structure, then we can actually learn one with high probability that is correct with high probability and use that structure. Okay, so that is actually really a nice result. Okay, and then I wanted to continue working on this, and then Tushant came along, and Tushant was my research visitor for a few months, and I started talking to him about this problem, and it was interesting because, you know, whenever you get a really good student, you know, you tell them, okay, try to do this for maybe a slightly more complex class of problems, like for fair division or for markets or something like that. But he went and just said, okay, well, here is a general framework for this entire thing. Okay, and this works for basically any game theoretic concept that you can think of. Like, it's a very broad framework. Okay, and basically the idea is you take the game data in like abstract sense. Okay, you can directly compute a pack solution that will bring you to this pack solution space while completely skipping over this pack approximation of the game space, and that's really nice. Okay, and here is what the general framework looks like. Okay, so we have a game space. Okay, and it's abstract. Okay, and you get observations from it, and these observations are evaluated by an unknown game to an abstract label space. Okay, so for transferable utility cooperative games, the observations were over subsets of players, and the mapping was a value for each subset to R, like Y equals R here. Okay, but it could be for Edoni games, it was a list of values in R, one for each player in the set. Okay, so it could be many different things. Okay, you want to find a solution in an abstract solution space S. Okay, and you have this loss function lambda that just says that the probability that we observe a loss is low. Okay, and I'm not going to get into the entire specifics here, but basically this required coming up with a new way of thinking about learning theory. Okay, so there's this very well-established theory of pack learning in machine learning. And what Tushan did was basically come up with a different alternative that captures this solution learning thing, okay? And there are some fundamental differences. I'm not going to get into them. You can read the paper if you'd like. But basically what you want to have is anytime that you can compute a consistent solution, like basically a solution that has no errors over the samples that you observe, and the solution dimension of this space is low, then you can make this guarantee work, this probability of getting low error on future samples using a polynomial number of samples, okay? And these results kind of apply broadly. They apply to everything I talked about before. They also apply to markets, to auctions, and other stuff. Okay, so that's a really nice broad framework. Okay, so let me just show you a few examples. Okay, it applies to market equilibria. Okay, so here the observations are of goods. Okay, so you have a bunch of food. Okay, and what you observe is like people, how they value these goods. Okay, so this person thinks that this set of goods is worth 7, and this person thinks that they're worth 4. Okay, and so on and so forth. And they're evaluated by unknown player preferences. Okay, what you want to do is you want to find some way of allocating the items to the players, and you want to compute a price vector such that the probability that another future sample set of goods is demanded by a player is low. Okay, where demanded by a player.
Excuse me, I hate to break in,
sorry.
but you're down to about a minute. Okay, just so you know.
Okay, sure. So I'll just wrap up here. So you basically, you can apply this here. You can also apply it to learning Condorcet winners. Okay, where you think about your samples here are just candidates, and you observe basically what you basically observe is a partial ranking of the players. Okay, and you want to find a candidate C star that probably beats any other player in a pairwise majority. Okay, so even in this simplistic setting, you can actually get some really interesting non-trivial results. Okay, and it applies broadly. It applies to learning optimal auction prices, to function maxima, to judgment aggregation, to other domains. Okay, and I like this because it gives you this nice unifying theory, okay, a consistent way of talking about learning game theoretic economic solution concepts, okay, and it's really easy to come up with new stuff, okay. So we've done this exercise like for Nash equilibria, for other things, it's actually relatively easy to do it, okay, and you don't need to make this complex, like, you know, concentration inequality, Chernoff bound stuff that usually appears in these papers, okay. It gives us a formal language to discuss it. And we actually use it on actual data. So we have like another paper, the working paper with Omer Lev, Wei Lu, Alan Tsang, and myself, where we actually try to apply it to real data, to voting data, with what I think is really interesting results. Okay, and there is a lot of future directions, interesting stuff to do here, like just talking about the quality of the solutions in addition to its back learnability. You want to make some quality guarantees. How do you compute solution dimension, and so on. Okay, so thank you very much. I'm also, if you want to talk to me more about what happens with me at UMass, we can talk more about that. So thank you very much. If you have any questions, I'm happy to take them now.
Okay, let's unmute our mics and give a round of applause to Yair.
I think that it is probably the biggest crowd I've spoken to.
Before we launch into the question session, let me just remind you that we resume next week at the regular time and place, meaning home. A learning framework, the speakers will be Nisarg Shah and Peter Biro next week. Okay, so yes. I see that Harris had a question.
Harris?
I think.
No, I didn't have any questions.
Okay, fine.
I was really clear.
Scrolling through the questions to look for them. Nisarg had a question. Does the O of n samples results hold without any monotonicity or related condition linking the values of different coalitions?
I think you can probably, I mean, what you're basically doing is solving a bunch of inequalities, like a bunch of linear inequalities. I don't think it requires monotonicity for it to work. I mean, it basically is like, it really is like it maps almost one-to-one to learning a linear classifier. So no, you don't need that. I mean, I don't know about whether the cost of stability result, like that guarantee would still hold, but the learnability part, like, yeah, that would work out.
All right, thanks.
Yeah.
Peter van Emden had a question, but I think I'll let him ask it since I don't completely understand it myself. Peter?
Okay, yes, I was puzzled right from the beginning. Since you were motivated by practical situations, if you use machine learning as a technique, you need a large sample of instances. But the instances also have to be sufficiently similar because you cannot just group any sort of games together. So what sort of, can you give an approximate description of how you select a class of games instances for which these sort of techniques are applicable?
Right. So we had a so here basically what you need to have is you have a you need to assume some kind of a hypothesis class, right? For at least for some results to hold. Okay, so the short answer to this question is I'm not sure because it really depends on the instance. I can tell you that at least some results hold like our instance independence so basically the hypothesis class is all games that you can think of, right? So that holds, for example, for TU cooperative games, and it all actually, surprisingly enough, so one of the results that we have in the EC paper is that the sample complexity at the very least of hedonic games is linear. Right, so actually computing the problem is computational because like computing a consistent solution might be complicated. Okay, like a low error, like basically one that's consistent with the sample, that could be complicated. That's like an NP complete problem, but the sample complexity is low, and that's again instance independent. Okay, but and this also holds for market equilibria. Okay, but again, the challenge there is to actually compute a solution and to maintain some quality guarantees. Okay, so I guess maybe a more interesting answer to the question, although it's not exactly the question you were asking, is that a lot of times learning a solution is instance independent, but learning a good solution that you can actually prove quality guarantees for is instance dependent, and then you just need to make some assumptions, right? And this is something that, for example, we did in the Knesset paper. Like, so we actually looked here and we tried to kind of like come up with a good set of hedonic games for which we could give at least some quality guarantees and stuff like that would make it map from the ground truth to the real world instances. So yeah.
So can I understand it that occasionally learning a solution is easier than solving the game?
Yes. Yeah. So that's actually, I mean, and more than that, right? Because like, think about, okay, so let's say that now you want to do something super simple. You want to compute a function maximum. Okay, so this is, you know, I give you some unknown function from Rn to R. Tell me what the function maximum is. Okay, and all I give you is a bunch of samples of the function and it like of points and the function's evaluation on them. Right? So if you went for you try to solve it using a pure learning theoretic solution, you would basically need to pack learn the function, and the function can be of arbitrary complexity. So that could be basically you'll need an arbitrary large number of samples. Okay, whereas computing an empirical maximum is trivial, right? You basically look at the samples, you pick the biggest one, that's it. Okay, so and that's not our result obviously. That's like known from prior work. From like the 60s.
Rita Laraki had a question. What is the assumption on the distribution?
That's actually a really good question. So, in order to compute so the framework that we present here is distribution independent. You don't need any assumption apart from the fact that when you do this partition into training set and training and test set, you do it in an IID fashion, which is a pretty standard assumption.
And Virginia Doe has a question about PAC NV freeness. Is this what they do in the NUR IPS 2019 paper called NV free classification?
Right. Yes. So this is kind of similar, but here I wanted to talk about the right. So PAC NV freeness. So the NV free classification setting. So there they look at a slightly more specific setup. But if you wanted to capture kind of like the full gamut of NV free of PAC NV freeness, right? So it's kind of challenging to talk about it. Like it doesn't exactly fit into our framework because what's the caveat here that you have is that if you look, okay, so let me scroll back, blah, 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 blah. Here, okay, so you want to have this error function, right? This lambda function that basically I give you that says, okay, for a sampled instance and a game and the solution, right? So here, think about like a TU cooperative game. It will be something like a set of players, the value function, and the pair of division, does this set of players get paid less than the sum of its valuation under the solution under this game, this unknown game? Right? And then it's a yes or no answer. It's not obvious how to ask this kind of question, for example, for envy freeness, because envy freeness is like this global property, right? It talks about like this global property of a game. And this seems to be more related to ideas in machine learning called property testing. Okay, so this is, again, I mentioned here in the related, like, somewhat related work. So there is a paper by Batachria and Day that kind of talks about these global properties in voting, and other works also talks about kind of a global properties that are more related to property testing. So not exactly pack learning, but another learning theoretic concept that we're looking into now, how to capture more general and interesting settings.
Okay, so Vince Conitzer has a question. Learning Nash equilibrium. Is this related to Wellman et al.'s empirical game theory?
For Wellman's empirical game theory, I think we looked at that paper and we saw some relations, but it didn't map one-to-one. I think if this is the paper I'm thinking of, I'm not sure. But the problem we had with Nash equilibria is that we couldn't quite compute the solution dimension for general Nash equilibria. Maybe it's worthwhile to look at more restricted classes, like, for example, I don't know, congestion games or something like that. But yeah, I mean, it's definitely, I think it's related, but I'm not exactly sure. I don't remember off the back of my head how exactly.
Okay, and Lirong has a question, but it's a long question, so I think Lirong will have to say it out loud if that's okay.
So,
are you there, Lirong?
Lirong? I can understand the question and answer it, but I think it would be better if you ask. Hi, Liron, how are you?
Yeah, hello. Sorry for hiding behind the screen. So yeah, I think it's more like an open question, and so this is really nice data-driven approach and in the economics domain. So, and I mean, like nowadays, like machine learning researchers are thinking about adding logic reasoning, combining logic reasoning and data-driven approaches. So one thing that I was thinking that might be very interesting is, sure, so it's very nice you can learn how they behave, learn this equilibrium concept, learn Condorcet winner, but what if they just behave differently and they are doing random things and want to help them? So then we probably have some economic principles there, just the counterparts to the machine learners, like logic-based reasoning. So I mean, it's really just like an interesting open question to me to see how to combine these two things and come up with.
It's an excellent question, and I think that this is one of the questions that kind of like haunts us. It haunted us for a while until we realized that it's not us, it's them. Like it's the data, right? So it's a pretty well-known thing, right, in machine learning, and it's a pretty standard assumption, right? So if this garbage in, garbage out approach, right, of saying like and this is I think what you're also alluding to, right? So if your data is bad, then obviously the models that you're learning are bad, and you will get bad classifications. You'll be massively overfitting to the data. If it's like, for example, like samples from a very small part of your data space, then you'll be overfitting, and like bad stuff would happen, right? And we, unsurprisingly perhaps, encounter the same stuff, right? So if, for example, in your cooperative game, right, you sample every time, your distribution is just sampling a single subset of players, and all you see is that one single subset of players, then obviously the answers, the solution that you will be providing for it will be fairly limited, right? And that's fine. But I do like this idea, and it probably does need us to assume certain things, like you probably would need to pay for that in terms of the generality of the theory, right? I do think one of the things that I actually thought about is maybe we can use some kind of like an active learning approach, right, of actively querying the model in areas that we don't know, right? So that would be nice. And then you get this active learning approach, which also ties in because a lot of algorithms that are already in the literature for economic solution concepts are already kind of doing that. But active learning is one direction. Reinforcement learning, which I think also sounds a bit like what you're saying, like you observe something, you try to teach them how to work better, you try to kind of like to assume some kind of a learner model that works in the background, and then they update their beliefs about what's going on, and then you continue. So I mean, reinforcement learning, I mean, it's been done by better researchers than myself, like Noam Brown and stuff like that, to applying it to game theory with great success. So I'm optimistic about that.
Thank you.
Right.
So, Yair, there are some more questions, but I think we should probably wrap up. So don't forget to take a look at the chat and for the questions that I did not get to. Let's all give Yair another round of applause.
Thank you very much.
Don't forget that we'll reassemble next week at the regular time to hear Nisarg and Peter.
So I can answer. I can actually answer Nisarg's question if you want, Nisarg. So if you're still around, Nisarg, I don't see him. He left. I'll answer him offline.
And there's also a question from Neil, which I think you may have addressed already.
Yeah, Neil, you asked a question.
That's an answer.
No, I tried to give the answer to another question.
Oh, because Neil is working with me right now on a paper, so it's. I mean, I'm happy if you have questions. I mean, but we already have a paper related to this topic, so. Anyway, thank you everybody.